All right. Here we go. All right. One thing I forgot to point out. Yeah.
It's because he's on the recording.
There's a little bit of a scratchiness. So the
You should not know.
all right. So it's a negative derivative. So if you look at this, the negative slope of this. So this is a parabola. Okay. Negative x squared. Okay. Take the derivative of that. It's just x. It's a linear. It's a line. It's linear, and it's negative, so it makes that positive. Good with that? Okay. Here we have x to the negative 1. Take the derivative of that. X to the negative 2. Okay. Good with that? Just trying to like make some connections.
Are you saying that goes the
Yeah.
second part goes?
This is the derivative of this gives you that. Or the negative. Thank you. The negative derivative. Negative derivative of that gives you that. Okay. All right. So coming back to charged rings. This is also on master. Yes. It is. Thank you. Okay. So the electric potential is a lot easier to calculate than finding the electric field because it doesn't have direction. It's a scalar. Does that make sense? That whole cosine thing that we did with electric field, pain, electric potential, it's a way lot easier. Okay? You don't even need necessarily have calculus to find the electric potential here if you recognize something. But if you don't recognize it, then you do need calculus. So go ahead and figure out the electric potential at this point here. From a charged ring. Great question. All of it. Okay, it has a whole, like, the charge on this thing is Q.
Thanks, got it.
Okay. If you don't, like, you really need to know how to, like, this is like a very popular free response question. Maybe.
Is the test going to be in like 2 weeks? Last week of February?
Somewhere in there.
Because we take the SAT March 1st, so just before that, right?
Huh?
Or no, they have the SAT.
Mine. No. Mine was physics is easy. That's
That doesn't want you to admit to not liking this.
I do love you guys. It would be not a white lie.
No, I do not love my AI. Take it from really far away so you can't find it.
Yeah.
Oh no! Now you don't not love us.
Yeah, now you
Double negatives. That means you do like us, and that's a lie.
and it's a lie.
Oh, you go. All right. Have we got this yet? I doubt it. All right. So a point charge is that. Okay.
Okay, you're doing it the hard way first. Got it.
Yeah.
Well, yeah.
Okay. So I want to integrate this.
Oh, actually, just, I'm pretty sure, yes, it actually does actually. You're right. Yeah, it's just the radius system.
But your mom does it.
Yeah, it's why I'm not.
What happens to lowercase
I
r?
did it last year and we almost all over.
Oh, good call. Thank you.
Food's great.
Is it okay if I write X as a point charge in my notes, or is that wrong?
X.
ACTS.
Oh. All right.
I don't want to have to erase all of my.
It's not entire. It does not exactly act like a point charge.
All right, it acts as a point charge.
Okay. So we're gonna pull out everything that's constant, which is everything.
Cram during lunch, not during your other class.
It's like the particular section plus the whatever.
Okay. So
Oh, the 2 pi r cancels out the 2 pi r.
this is why you don't need calculus to do this problem, because everything's constant. All the charges are the same distance away from this point. And we're not looking at components.
This is
Okay.
It's a non-directional thing.
Oh, it's 2 pi r.
So it becomes, so when you stick this in, you got 2 pi r, that cancels with this one, so that annihilates that. So all that stuff. That's our answer.
It's just the way he said it. It's funny to me that he can put that. It's funny to me that he can put that with that. Well, then he goes that in my heart.
Okay, that, are we all right with there?
Yeah.
Okay, so
I
We
just
ha-
made it a point charge.
we have an expression now for the electric potential. Okay,
Oh man, we already solved it.
we did, but this is the easier way to do it.
Okay, that's why I was wondering.
The electric field is equal to the derivative
Oh.
of this. So I'm going to do it with respect to z.
Don't be mean.
You all right with that?
KQ is a constant, so
Everybody okay with where I'm going on this one?
Yeah.
Okay.
DZ. No.
Okay. So
You're gonna replay it. Okay, I'm coming down now. I'm coming down.
Wait, why?
no.
Usually I know.
You dropped the negative.
Oh, good call. Thank you. R squared. And so I'm going to take it's been a long time since I've taken a derivative. All right, so
You forgot to multiply by You forgot to multiply by negative 1/2.
where's the 1/2?
Oh, never mind, because the wait.
2 and the 1/2 cancel.
Yeah, sorry.
Good? Okay,
Yeah.
moving on.
Where's the?
So doing chain rule. Oop, 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 oop. Thank you. Okay. So that, this cancels with that. So we find electric field. Yes.
How did you do, should there be an equal sign between DDZ and negative KQ?
Nope, there should not be.
Oh, okay.
Sorry. I couldn't remember how to write.
No, you're fine. Yeah.
You would use parentheses or a bracket. I would recommend a bracket, but I don't like them, so I would use parentheses.
Okay. So we end up with
Yeah. Why is it a negative 3?
Yeah, shouldn't it be negative 1/2 there?
Say you use dash too much. Say you use dash too much.
But
No, but isn't it just a derivative of b?
if you take the derivative of that, that becomes 2x to the 1.
Yeah, I got the vibe that you derived.
Yeah.
No.
Yeah. What?
Isn't that b?
that is D.
Sorry. Good call.
I was like, I know what happened.
Yeah, I don't. Where I was confused with the.
Sorry.
Oh yes, sir.
That's 1/2. Thank you.
And then that should go to 3.
There we go. No.
And then it's not going to be negative 3, obviously.
Correct.
No.
I thought you meant negative 2 times.
My bad.
You dropped the negative. You dropped the negative again.
Okay, so we are all right, and we all.
The initial negative and.
Oh, yeah.
Oh yeah.
Nice.
This is why when you get to the end, you ignore whatever negative you have.
It's like that's what you mean.
So we got K, Q, Z. Over.
How are they not?
Hey, that's me. Oh, that's true.
Guys, me and Spiral so hard at Nelson's yesterday. Let's try it.
That's what the Z.
All right. There it is. And this is how you're going to derive the electric field due to a ring charge of a ring of charge on the electric. Hey, nice. On the AP test. Micah.
So this is kind of the same as chain rule comparing
Yeah. This is how I would do it versus doing the integral with the cosine and all that stuff. Like that required you to like pull out trig identity integrals, like yeah, out.
Where did the second negative come from? Or maybe the first one at the top?
This one's this part of the equation.
Okay, yeah, I got that.
And then this one came from when we did the derivative, took that here.
Okay.
So that's negative, canceled with that one.
Got it.
Can we get a TI, like 89,
Sure.
on the AP test?
Yep.
What?
Nice.
Okay, allow it. Okay. No.
I've not started that calculator.
No keyboards.
Wait,
Is that actually a calculator?
There is. There is it. I mean, I think they did away with it, but there is a 90 that like I was like.
So I'm going to make one of it.
Okay. So back in the day, we solved this just with like point charge, and we did it with electric field, and we did the cosine, added all that up, took the integral, and we got the same expression. This way is way easier. And then taking the derivative, in my opinion, that's my preferred methodology. Okay. So, big picture for this whole entire static electricity unit. Okay. You can either do what we did in the first part, or just hardcore gutting at Coulomb's law,
Yeah, I'm not doing that.
or electric field. Okay. Divide up the charges, do what we did. Okay. Another approach, and which I'd highly recommend, would be using Gauss's law. Find the field using Gauss's law, and then use that to find the electric potential, find the integral. Okay. And then the third approach, depending on what you're given, these are like the different strategies though. If you're given electric potential, you can find the electric field by taking the negative derivative.
I'm pretty sure you should be able to do it. I'm pretty sure you should be able to figure out the electric potential in all the cases where you can't use Gauss's law. So you have those rings, which electric potential is nice. I'm pretty sure with lines electric potential works as well. I could be wrong.
Yep. Good with that. Cool. So big picture. Probably the most important slide for this chapter.
Bradley, will you post that to Discord?
Yeah.
Big picture.
Smiley's big picture. Smiley, why aren't you in the Discord?
No way. I do not want to be in the Discord.
It's got your face on it.
I'm sure it does. Not surprised.
Yeah, Mr. Gilmore.
Mascot. That's fine. He can.
He's grandmaster.
I'm gonna make it the big picture. It's gonna be a private channel that everyone can access.
Okay, here we go.
Except Calvin.
It's a small picture. It's just the same picture, just small.
Just compressed. Yeah.
Tell your neighbor.
I don't have it yet.
Dang it.
Yeah, it's that one. It's probably that one. That one. It's definitely that one.
I love that. Heck.
Correct answer is
D.
D.
Wait. Oh yeah, D.
Okay, 1/2 base times height. It's a negative part of the equation. So you have electric field as a function of position. You're going to find the potential. You find the integral area under the graph. Okay. Tell your neighbor.
Wait, strength is what?
Strength is magnitude.
No, that does not change your answer.
Daniel.
Correct answer is A. Okay, it's the steepest. It's the derivative, the negative derivative of that gives you electric field.
Wait, there's a problem I have to do first. We're gonna do the thing.
Thumbs up when you have a guess.
It's definitely a guess.
Have a conversation.
I don't know which one it is.
I'm thinking E, and my explanation for why it's increasing speed is because the electric field is constant, basically, because the slope is constant. But the electric field is exerting a force, electricity force upon this electron, which means it's going to have an acceleration.
Yeah, okay, fair enough. Okay, the reason I was doing B is because I didn't realize it was right after, and so I was looking at that and I'm like, okay, that's definitely not constant. So that should counteract the fact
Even
that.
then, it's still
Yeah, no, it should
exerting
still
a positive force upon it.
Yeah, no, yeah, it should still, yeah.
That's super nice. It does just move that potential.
Correct answer is
E.
E. Good job. Okay, electrons go uphill to a higher electric potential. Okay, there's an electric field. It's in electric field, therefore it experiences a force. Therefore, the speed is not steady. It is increasing. Okay.
Move that. Maybe.
Ooh.
Bless you. Bless you. Tell your neighbor.
Hey,
I got B, but I don't know why.
Oh, yeah.
The slope is negative. The slope of the line, if you were to like copy it. And then
No, I
negative
forgot
that,
it was 0,
negative
4.
Correct. Correct answer is A. I would say you can do if you plot that, you can do that. The way my brain works is like electric field's pointing downhill to a lower electric potential. That makes sense? Okay, so Kirchhoff's loop rule actually applies not just to circuits, but to anywhere in space. Craziness. Okay.
But okay, so that's why I worked with circuits.
Okay, so it's like whatever your path, the loop, the change in potential is 0. Okay, so voltage gain equals voltage loss.
And junction rule doesn't really make sense outside of circuits.
Correct. Okay. Is everybody good with D? Okay. Path independent, doesn't matter. Started here and into there. All right. So here we go. We have a conductor that is charged. Okay. The net electric field.
What is S supposed to mean?
Distance.
Okay.
Okay. So the net electric field in here is 0. Good with that? Okay. So the change in electric potential difference, or voltage, we'll just go electric potential difference is equal to electric field times distance. On the most basic, it's constant. If the electric field in here is 0, then the electric potential difference is 0.
Yeah.
So as we go from this point to this point, there is no change in electric potential. We could do that anywhere inside that conductor. So the result is that all points on this conductor have the same electric potential. That is a really good fact to know. Okay, on a conductor, all points have the same electric potential in static electricity. Okay, that's a really good fact to know. All points along a conductor, on the surface of the conductor, have the same, actually, throughout the entire volume of it, have the same electric potential. Okay, good with that? All right, so if we're drawing equal potential lines, so if we had like a constant field and then we dropped like a ball or a cylinder in here that's metal, that's going to warp the electric potential. So like here, this all is the same electric potential. So like warps that. That's because of the polarization that happened within. It creates its own electric field. Electric field lines give us the net, the total electric field in space. Okay. So electric field lines are doing this. Okay. Equal potential lines are the elevation. Okay. Something similar in there. Good with that? Okay. So the entire outer surface constitutes as an equal potential line. Okay. So by definition, electric field lines must be perpendicular to equal potential lines. Okay. Therefore, all electric field vectors are perpendicular to the surface of a conductor.
Now you might see why things. Never mind.
Thank you. Okay, good with that? So these are just some factoids for a conductor. Not an insulator, but a conductor. Okay, so if we have a charged conductive sphere, this is not news to us. Electric field inside is 0, outside it acts like a point charge. For electric potential, acts like a point charge on the outside. On the inside, it's a constant value of electric potential. So if we were to revolve this around the y-axis, this is what the landscape would look like for a charged sphere, conductive sphere. It'd be a plateau here. Does that make sense, Sam?
Why is it not 0 if electric field is 0?
Great question. So electric field tells us I'll use R, tells us that there is no change in electric potential.
We'll use that electric potential has to be whatever it was.
Okay, does that make sense? You can still have electric potential,
There's no slope.
just no slope, no change in it. That's a great question.